In this second day of Colloqium series, Robert will give us the second talk about computational physics and atomistic modeling, a versatile window into materials and their properties. So, to Robert, time is yours, please.
Thank you. Thank you. Is the audio level okay? All right. Thank you. I hope also people on Zoom can hear me well. Thank you very much for the introduction and the opportunity to give presentations here at ITB. I have been enjoying my time, and I'm sad that I will have to go back to South Africa soon. But before I do, I want to take the opportunity to tell you a little more about my research and computational physics in general. Given the audience, I probably, how we say, preach to the converted when I try to make the argument why computational science, and in my case, computational physics, is the way to go in the future in terms of basic and advanced research. In the meantime, I have a short outlook. So first, I will introduce a little bit about myself and material science in Johannesburg. I'm going to go a little bit into, oh, now it works. Perfect. Thank you so much. Give a little bit background about the principles of atomic scale modeling. This is going to be a little bit repetition from yesterday. So those who were attending yesterday, I'm sorry for that. And I will give some examples based on my own research. But of course, it's a very wide world, so there are many more things we can do. Okay, for introductions, I'm originally from Germany. I grew up in a rural area of Germany. Doesn't work. At the Baltic Sea coast over here, and I studied in a small town called Greifswald. It's a university town, 500-year-old university, very beautiful. Unfortunately, not quite as prestigious as it used to be. Nevertheless, I did my undergrad and PhD there, and then I went to South Africa for a postdoc, which is something I usually recommend to all aspiring scientists. Whichever country, whichever university you are to do your undergrad, at some point leave. You can come back, but it is important for a scientist to have a broad mind and a variety of experiences. And whenever you have a chance to do part of your study somewhere else, I think it's a good idea to take it and widen your horizon. I got kind of stuck in South Africa, and I've been working as a senior lecturer at the University of Johannesburg since 2018. I'm currently also doing some administrative roles there too. South Africa, this is the southern tip of the African continent. We find Johannesburg at the almost top right corner, not quite center of the country, which is our population center. And this is where we are located research-wise. We're a little bit at the end of the world in the sense that the southern tip of Africa is very far away from most research centers in Europe, America, and Asia. Okay, 3 pictures of Johannesburg. Johannesburg is a metropolitan area of about 8 million people, which for African standards is fairly large. And despite having the typical concrete city center, we actually are the largest man-made forest in the world because all of its suburbs have vast amounts of trees, which makes it actually quite a beautiful place to live in. And we have 2 large universities, research universities in the city, more in the region, the University of Johannesburg and the University of the Witwatersrand. The latter just had its 100th year anniversary last year, so about the same age as ITB. Material science is actually very popular in South Africa, and it has been so for a long, long time. I think the first material science or the first universities actually were, or at least one of the universities started out as a mining college. And first material science, I think, was done at the University of the Witwatersrand, which is in Johannesburg these days, and funded by De Beers, which is the well-renowned diamond company. We have a number of different universities active in material science. We have a Center for Computational Modeling. We have a university which focuses a lot on material synthesis and characterization, and one for which is very heavily invested into semiconductor technologies. And of course, many more things which I forgot, especially engineering faculties. We have lots and lots of things. Most importantly, though, and this is the funding, the base of funding for most of my research, we have two big centers of excellence in material science in South Africa, which, as you can see, support a number of different areas. For me, most importantly, we are very active in renewable energy research, energy generation, and energy storage, which I think is helping us along with the UN Sustainable Development Goals, which we currently have to focus on for human sakes, kind, and of course for funding. Okay, so what is computational physics and why should we care? That is probably not very difficult to understand, so I will not go into details too much here. Computational physics is just done, physics done with a computer, basically as a third branch between theoretical and experimental physics. It has been becoming more popular over the last few decades. And in the past, it was more associated as a sub-branch of theoretical physics, but has evolved to become its own thing over the last few decades. And we sit in between because I can say that as a computational person, I run a numerical experiment, right? I can interpret what I'm doing. If I have a piece of software, I set it up to emulate certain physics behavior, and I run it. That is an experiment. I take the data, I analyze it, much the same way I would do an experiment. I have to do an error analysis, same way I would do with an experiment. So we are on that side in a way. But of course, we are also dealing directly with the equations, right? We are selecting equations, physics equations, parameterize or solve based on certain assumptions. That is our connection to theoretical physics, right? So we're very much sitting in between these two and hopefully getting the best out of two. And of course, we use tools. The physics is just the application. We have here the Center of Computational Science, which I very like that this is here, because of course, it's not just physics, it's biology, chemistry, all these things, yes? We're using the computer, we're using the mathematics, the applied mathematics, these methods to solve problems in our sphere of expertise, right? And that is really a very powerful thing. And I think having a background in education in computational science is very beneficial for any student these days. Okay. We must always be a bit careful when we're talking about a computational scientist, because that can mean a lot of different things, right? Because the process starts from the very much mathematical side of devising an algorithm and setting up a mathematical model, up using then going to the programming side of implementation, and of course then the experiment itself. So not all computational scientists are created equally in that sense. Everyone has a different expertise, and that is a strength, right? Not everyone can be good at everything, right? We need to work with people, right, to gather all the best from all areas. Okay, let me skip this too. As I said before, as computational scientists, we're always in between, and that has certain advantages and disadvantages. So for example, in theoretical physics or other theoretical sciences, we often deal with things like differential equations, right? That is also in computational physics the most common thing we have to solve. And differential equations, for example, as other things, become very tricky to solve analytically at some point, right? So if we want to solve a differential equation analytically, we have to usually approximate, throw terms away, do linearization, whatever not. These things are bad. We might lose important behavior. With the computer, we have that problem to a lesser extent, but of course, numerics itself produces errors. One big advantage over experimental sciences is that in the computer, we obtain the solution in a more usable way. Any experimentalist has very limited access to data, right? As a physicist, if I'm doing experimental physics, I measure a spectrum, I measure some most power data, I measure some XRD or whatever. This is secondhand data, so to say. We never have the actual information about the system. We can infer from the data how the system behaves, but this is indirect in a way. We don't have that problem. If I work in a biological or even social science, the process I want to model may take years or decades. I cannot collect much data there, right? We don't have that problem in a computational approach. So this is many reasons why I think we should have a heavy focus in our research universities on computational science. Okay, so enough of that blah blah. Let's go a bit more into my specialty, and that is computational material science. And there we are forced again to consider a number of philosophical problems, right? So we know that if we're interested in materials, this is on the scale of, say, meters, yes, macroscopic objects. But we know that material properties are in the end determined by quantum mechanics, right? Quantum mechanics equations we have to solve. But we also know that there are several orders of magnitude in between and lots of things which can happen. Defects, cracks, inhomogeneities of the material, and so on. And that is, in terms of research effort, I think one of the bigger challenges for the next few decades to get the multi-scale description of materials correct. Of course, that also requires, because these different scales are governed by different types of equations, that requires different numerical methods, which require, again, different skills. So it's not always reasonable to expect that the single scientist will be able to do all these simulations on all the different length scales by themselves. Okay, so if we now decide that we want to go quantum, then we use the Schrödinger equation. That is what is governing our system in quantum mechanical realms. And that is a second order differential PDE, where the kinetic energy in the T terms is a second derivative of the positions of the atoms and of the nuclei and the electrons E. And we have here interaction terms which depend on the coordinates between atoms and electrons and so on. So it's a coupled system, which makes life very miserable. So we do several steps. We assume, for example, that the time scale of the motion of electrons and nuclei is different so that we can separate out the motion. And we only consider the electronic problem for a fixed set of atomic positions. That is usually quite okay, but sometimes this is going to produce problems. And then if you say, okay, now we just look at the electronic problem, depending on what we're going to do, we then use different methods. If you're interested in molecular dynamics, we can usually, so time evolvement of the motion of particles, chemical reactions, that sort of thing. We might want to parameterize some analytical function like a Lennard-Jones potential to roughly describe the interaction that is very fast, but very inaccurate and might not be transferable between different systems. Or we might choose to solve the Schrödinger equation using one or the other set of approximations, like density function theory, which is the method of choice for material science usually, and Hartree-Fock-based methods, which is usually the choice for chemical application. All right. Let's maybe not go all that into detail here. I just wanted to originally to go a little bit into how we set up these kind of equations, but I think that might take away too much time now. So let me skip this. If there are questions afterwards, please go ahead. And I will just go over these slides because I want to show more pretty pictures than equations. I think that is better for most people. All right. The results I present here in any ways are based on density functional theory, which is basically a reparametrization of the Schrödinger equation, making two assumptions. Assumption one, I don't need the 3n coordinates of my electrons. I just need a function rho of position r in space that will describe my electron density, and that is sufficient. I don't need to track every electron. I just need the electron density. Electrons anyway are supposed to be delocalized most of the time. So yeah, that sounds fair. And that is an exact, it's not an approximation, that's an exact rewrite. So we're happy with that. And the second one is the nasty one, which is why density functional theory, while being very popular and successful, is actually a bit pathological as a method. We replace our interacting electrons with non-interacting electrons, because interacting electrons means that we have a differential equation or a set of differential equations which are all linked, right? Very nasty to solve. But if we just say, oh, we separate this, these electrons are not interacting, then the one potential term goes away. All the electrons are just moving in a mean field given by the density, right? And that is some external potential coming from somewhere. We're not looking at this. Much easier to solve. But the resultant is that the electron, the meaning of an electron is gone, technically, right? These are just pseudo particles in a way, artificial ones. The only thing which ever is guaranteed to work is the ensemble, right? Because the density is the correct density. So everything which relies on the ensemble of the ground state should be fine. Everything which relies on a single electron and what it does, probably you have to be very careful. Okay. So we are basically, I didn't talk about the first one, but the first method is the more accurate approach the chemists use, but it scales horrendously bad with the number of electrons. For example, the SDT method, coupled clusters with singles and doubles and triplets in perturbation theory, scales with the 8th power of the number of electrons in the system, right? So this goes very, very badly. Whereas a density functional method is not as accurate, and it cannot be converged as easily to a proper correct limit. It scales only with n log n or n squared in the worst case usually. So we are happy with that, but there are a number of issues with that method making it much less accurate, which will come back to bite us soon. The good thing about any of these methods is we get the wave function. In quantum mechanics, all the information about the system is contained in the wave function, right? And because we have the wave function, technically, we can calculate any observable. Basically, any operator which is Hermitian, we can just do a bracket with the wave function and we get an observable, whether or not it's experimentally observable too is a different story, but we can just do that, right? So this makes this kind of method very versatile. You can come up with a physics problem, which has not been done before, and very easily add to the software your observable and get the result, right? You don't have to invent a new theory for that. So that's a very, very powerful thing to do. In all these different things, my specialties are usually the spectral things, optical and infrared Raman spectroscopy, which I will be talking about most. Okay, but before I do this, let's do some other things, not spectroscopy. Okay, first colorful picture. What did we do? We were looking at carbon nanotubes. All right. This was a big project where we looked at carbon nanotubes and how they react under pressure and what happens if we introduce defects in the carbon nanotubes, how this changes their behavior and so on. And this is a simulation. This is actually not a DFT simulation, so I'm a bit cheating here. This is actually done using molecular dynamics, but I hope you forgive me. Where we just made a very simple experiment. You take a bundle of carbon nanotubes in hexagonal close packing, and you put it under pressure, right? On the on the y-axis, you see the volume of the bundle and per unit cell, and you see on the x-axis the pressure applied. It goes from 0 to 30 gigapascal. So 30 gigapascal is huge, right? It's a very large number. And you can see that on the orange line, carbon nanotube starts out as round, right? And if you apply pressure, it first becomes oval, but the volume decreases in a linear fashion with the pressure. And then where the first black arrow is, we see at 15 gigapascal, there's now all of a sudden a dip, right? At that point, the structure slightly collapses. It cracks a little bit, it moves. And then again, it now has this oval shape. Before, the nanotubes try to stay round. They just become closer together, the atoms, right? But at some point, that's not feasible anymore because they become too close. So they need to lower the symmetry. And this is actually a very common thing which happens if you put a material under some kind of stress. It lowers the symmetry to get more degrees of freedom to get away from what you wanted to do, right? This happens very easily. So it goes into this oval shape. And then again, you have a linear trend, right? It just becomes, it stays in this oval shape, just it gets closer together. And then you see here at 25, the next point, we went to this racetrack, almost parallel sides, and then all of a sudden the carbon nanotube completely collapses, right? Now your system is destroyed, right? You squeezed it to powder. If I look at the blue line, this is a nanotube where we put in some defects, right? This is not a perfect nanotube. And now you see the behavior is very differently. The gradients are different, the points of transitions are different, right? Message here being, well, obviously, if you put defects in a material, it becomes weaker, that's obvious. But the story I'm trying to say, and also with some other examples I'm going to bring up, what we usually do in material science is, at least in the past, we take a perfect material. We make a perfect unit cell of a perfect material, and then we compute optical properties, hardness, phonon dispersion, whatever not. An experimentalist will never measure this. A real material is never perfect. Understanding, it doesn't mean that the calculations are useless, right? It's a reference value. Understanding how a defect, an impurity, grain boundaries, how these affect the macroscopic properties, that is the challenge, right? Because this not only makes us more comparable to experiment, right? But it also helps us understand what are the bottlenecks, right? If I know that a certain kind of defect destabilizes this carbon nanotube, is there a way I can grow the carbon nanotubes without that defect? Maybe then I risk more defects of a different kind, but maybe these are not so detrimental to the stability of the system, right? But you can only make these discussions if you first do this. All right. Second example, again, talking about defects. On the left, you see a single layer of graphene. And I introduced a little bit of defect there, Right in the center, you see that I don't have hexagons. I have 2 heptagons and 2 5 and 7. Hepta is 7. Pentagons. Right, pentagons. Right. So we basically just rotated 2 atoms by 90 degrees to create this defect. Very common in carbon nanotubes, also in graphene. It appears naturally when you just grow them in whatever fashion. All right. You can't avoid it. Does it have any consequence? Well, I hope you can see it. It might be a bit too small. One of the more famous properties of graphene is that it's a semi-metal, so there's no band gap. So band gap would be here at 0. It has a Dirac cone. So basically, it's a 2D material. So in the reciprocal space, there are 2 coordinates, so we can make a nice cone. And there's a linear dispersion relation in there. That, for example, has consequence, like theoretically, what is the mass of an electron, effective mass of an electron in a material? It is the second derivative, or proportional to the second derivative of the energy with respect to the momentum, the crystal momentum. If it's a linear dispersion relation, I get a 0, right? So basically, that means in the end that if an electron has a certain momentum but no mass, it would have infinite velocity. That sounds a bit dodgy, doesn't it? Doesn't stop theoretical physicists from thinking about it. But now, if I just make a slight change in this crystal, and I don't know, I hope you can see the green and the red line. You can see the red line, certainly. I'm not sure you can see the green line. I can't see it on the screen. You see the green line does have a different dispersion, right? It's a different gradient, A, and this is now very difficult to see, I'm afraid. At this point here, it doesn't do this. It goes, and then it does this. It becomes flat, right? So now the whole theoretical framework people spent a decade building for, graphene and linear dispersion relation and what possible consequences this might have. Yeah, it doesn't work in practice. It's a nice model. Helps understand students some mathematics. It's okay. All right. Another beautiful example, I just added quickly at a direct request to include this slide. We recently, a year or 2 ago, had a nice project at my university, actually run by the engineering department. I was merely playing consultant on this project, where they were working on desalination membranes. So desalination, very important issue currently, because many parts of the world do not have enough fresh water, right? So desalination is an issue. Having done desalination in a cheap fashion, which doesn't take too much energy, is important. So what we want a membrane, right, which allows water molecules to diffuse through, but not ions, right? So basically the salt water and whatever you want to have in there, right? So the setup, as you can see on the bottom right, would be, in this case, you have in yellow molybdenum disulfide sheets, where, for example, the middle one would have a little hole in the center, as you can see in the middle bottom. And then you would use the left sheet as a piston and just press the water through, right? You have to use a little bit of force, right? Okay. And then what we can look at is, okay, depending on how big the pore size is, aka the hole in the molybdenum disulfide, right? How much of the ions in the system which we don't want to go through are retained on the left side, right? And we can see that in this kind of setup, this is about, say, 70 to 90% retention. So you have just 2 layers of that into a file. Now, the tricky part is that if we do this with molecular dynamics, in this case with lamps, the interaction between the ions and the molybdenum disulfide is not going to be represented properly, most likely. So we have to double check with DFT, atomistic simulations on the very left, to see what is actually the interaction of different ions we find in the water with the surface of the MOS2, because we don't want things to happen like that the ions get attached to the surface. We don't want any chemical reactions happening there, right? So we need to have the different methods to of different scales to cover all the different processes. So this is basically the minimal setup of a multi-scale model, right? In a very crude fashion. But yeah, it was fun to do and actually very relevant. Okay, next subject. The following few slides are a bit of a repetition from yesterday. My apologies. I have to fill the hour somehow. I want to talk about some of the applications which are close to my heart, and that is infrared spectroscopy, where we start with basically this is based on the motion of the atoms in the crystal, which lowers the symmetry, which gives rise to polarizations and dipole moments, which then produce visible spectra. And here the crucial part is, so this is just a standard harmonic oscillator setup, right? Not so difficult, I hope, to understand. The tricky part is, or what we actually do numerically, is in line 2, we have the second derivative of the energy with respect to displacements of atoms. That is what gives us a force constant, which is basically the matrix we have to diagonalize to get the energy or the vibrational eigenvalues. Okay, so as I said yesterday, that is then if I have n atoms, each atom has 3 coordinates, 3 n coordinates. Second derivative, if we do a finite difference method, second derivative, central finite difference, needs 2 extra points, right? 1 plus 1 minus, assuming that the function is not symmetric, right? So I now have 3 times 2 times n simulations I have to run, right? So that's a lot more than usual. If you have 400 atoms, that comes up to a lot of simulations, right? If I assume that my one simulation scales about with n squared number of atoms, or electrons in this case, you end up with something like n cube scaling, or at the very least n cube scaling of the method. So that's not so great. So basically, we currently reach out at like a few hundred atoms, what we can do unit cell wise. All right. And there are then a number of things we can do with it. This is something I showed yesterday. Did I? I did not. I did not. Sorry. I get confused. There are a number of things we can do with it before we even go to spectroscopy as such. So you see here on the screen measured Raman spectra. I didn't tell you yet what Raman spectra are, but it's basically showing us the vibrational modes of diamond with a few defects in it. This is experimental data, and a colleague of mine did these measurements. And what you usually expect is something you see on the left, where you find one big peak labeled 1638. That is, I think, usually supposed to be a double carbon bond happening there, and most people measure just this one peak. For whatever reason, he managed to measure 2 peaks, which you see on the right-hand side, that one and just one next to it at 1658. And now the question was, where is that one coming from, right? So, of course, now you can't just, and that is what usually when experimenters come to me, they say, I have a problem simulated. And then I say like, okay, what is your problem? I don't know. So that is always a bit of a tricky part. You have to have a model first. You have a problem, you have to have an idea what might be the reason, right? And that colleague was very nice. He had a guess. His guess was that he has a defect where the atoms there which are gray, these are missing in the crystal, these are defects, so that the atoms which are slightly shaded darker greenish, that those then have a different chemical environment, right? Okay, this was his assumption. And he assumed that if we have this, then we will see this double peak he saw. And this is something I said, oh, no problem, I can do that. It takes me half a day. And then I get all the different vibrational modes of that system. And I see 1600 reciprocal centimeter mode. So no, that's not. I have no idea what the right source is of that effect, but I certainly showed that his idea was wrong. That's already quite satisfying. Sometimes that's all you can do. Prove people wrong. Easier than coming up with a good idea. Okay, so this is still an open problem. That's why I don't go any further, because we still don't know what it is, right? It's not so easy to come up with separate new ideas here. Okay. The reason we are interested in vibrations is because it gives us markers for the structure of a material. If I have, for example, a carbon-carbon bond, I know it will always be somewhere in the energy range between 1,000, 1,300 odd reciprocal centimeters, depending on the chemical environment. If I have 2,200, it's a triple bond, something like this. If I have something above 3,000, it's always a hydrogen with something else, right? So this is a very good ear marker, a very good thing for us to have, because usually the problem when we talk to experimentalists as computational scientists is we don't have a common observable. We have to ensure that the system the experimentalist is measuring has something to do with the system we're modeling. It's never going to be the same, yes, but at least we have to make sure that there is some good relation. So we need to have at least one, preferably more than one observable, which both can access. And one of these is, for example, spectroscopy, infrared Raman optical spectroscopy. So if we have an experimental spectrum and we have a simulated spectrum and they're the same, then we're very hopeful that we can get the right answer. So in the infrared region, there are two types of measuring the spectrum, aka the vibrational modes. Infrared, Fourier transform infrared spectroscopy, and Raman. The first one is actually very easy. It doesn't require any additional softwares or anything. We just assume we have a Lorentz oscillator. Lorentz oscillator has a plasma frequency. That plasma frequency scales with the charge. And what is the charge in this case? Well, it's a dipole moment. When we have something vibrating, we create transient dipole moments, and these are basically proportional to how easy this mode is excited with light, for example. All right, that's easy, right? We just make our second derivative of the energy with respect to electric field and displacement. We get a dipole moment. Okay, that actually is an easy option. Quantum espresso, you just tick one more box when you do your pH.x. Let's not talk about that in detail. You can use it to get fingerprints of different materials, right? So here is a bit tricky to see online, I'm afraid. I have some silicon dioxide and a few other materials, some lanthanide and some other materials which you can find in glasses, for example, right? These are not glass unit cells, but these are materials you use in glasses. And now basically, if you take the spectrum of your glass sample, your waveguide, for example, at different positions, you measure the infrared spectrum, and you then can see, okay, this peak here belongs to silicon dioxide. This peak here belongs to aluminum fluoride, right? And then you can see, okay, is this a homogeneous sample? Do I have the right ratios of everything in there? So this is a very cheap and quick thing to do experimentally and numerically, which is the perfect thing to have. One thing which is easy to do experimentally and very difficult to do numerically is Raman spectroscopy, right? Which depends on a bit more difficult approach. But basically, what we do is, what we need to consider is the interaction of the vibrations and the electronic states. And we have to come back now to one of the earlier slides when I said we set up DFT such that we assume the atoms don't move. right? That was our first assumption. So this is actually always wrong because we know in quantum mechanics, the harmonic oscillator solution, the ground state, right, it has not zero energy. The ground state has what we call 0 point energy, is always slightly larger than zero, which means even at 0 Kelvin, no energy in this, no temperature in the system, the atoms are always moving, right? And even more so if we have temperature. So we want to take this into account somehow. And basically what we're saying is, if hopefully everything is adiabatic, if I just place my atom, aka I make a gradient with regard to the position of the atoms, or displacement of the atoms u, then the effective potential my electrons are moving in will change, right? And how do we measure then in physics the resultant effect? We just do an inner product, bracket. I have two electronic states, I and j. I just take this operator inside, I do the bracket, and this is now defining the interaction between state I and j as, what's the right verb? Produced by the vibration L, right? Which is encoded, EL is the direction in which the vibration goes, right? We have to take the gradient and then project it into the right direction. Okay, so this is basically the ingredient, the very difficult to compute ingredient that can take a month or so to get that computed. But if we have something like this, right, then we can do Raman spectroscopy, which basically, how does it roughly work? We have an electronic state I, which is this parabola at the bottom. And in this electronic state, we have different levels of vibration. These are the ones we want to probe. We have on the top a parabola, which is a different electronic state, also with its distinct vibrational modes. So we shoot now a laser at the material, which is in the lower one. It will get excited into the higher state. And then afterwards, it will, after some time, de-excite into the original electronic state again, but not necessarily into the same vibrational state. And if it does go to a different vibrational state, then the light we measure after has a frequency difference compared to the light we shot in. And that difference is basically the energy of the vibrational mode, or difference between energies of vibrational modes, to be more precise. And that's the information we wanted to have. If we do this for, that was a simple explanation. If we do it more appropriate, this looks a bit more difficult. But basically, it boils down to, we have an excitation, an optical excitation. That is one bracket. We have some phonon interaction. So a phonon is either created or destroyed. That is a middle bracket. And then we have a de-excitation, which again is an optical process on the right. So we have three consecutive ingredients we have to compute and multiply, and that gives us the Raman intensity. Okay, and that one we can use. One or two examples. Going back to our carbon nanotube experiment we had earlier, right? One of the things we wanted to do is we wanted to see if we put the carbon nanotubes under pressure, whether we can make them not merge, but link somehow. Reason being, carbon nanotubes are interesting technology-wise because they're very strong. They're very difficult to rip apart, but they're also very wobbly. And different carbon nanotubes, they're only interacting via van der Waals interaction, which is very weak. So if you have a fiber of carbon nanotubes, unless you twist it really hard, the nanotubes can easily go past each other. So the weak point of a carbon nanotube material is supposedly the weak interaction between the tubes, not the strength of a single tube. Okay, so but if we can maybe introduce some interlinking, some chemical bonds between different nanotubes, then maybe we can solve the problem. Okay, so we do this experimentally. We take our powder, we put some radiation on it to create some defects. We put it in a diamond pressure cell, put it to 20-odd gigapascal or 30. We depressurize, we measure the Raman spectrum. Now, how do we know that we actually produced these interlinks, right? That we don't know. but we have the computer, right? So I can take this. I first do, say, a molecular dynamics simulation on the left, perfect carbon nanotube, blue Raman curve on the right. I do my magic, defects, blah, 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 numerics. I have my chemical bonds. What is my new spectrum? It's the red one on the right. So now if we're lucky, the difference is so significant that experimentalists can compare their original result to their after experiment result, and now can see whether they can find the same pattern, the same kind of change, which would indicate that they found what they were looking for, which in this case, we are certain that it worked. Okay, that was a very nice thing to do. A second application, which is of interest, is, or which is actually something I did more because it was challenging. I wanted to test the new code I wrote for the Raman spectroscopy. How big can I go? Because I said it scales very badly with the number of atoms. So usually we do like a dozen, 50, whatever. The one you see here is 400 atoms, 440, something like this. Took a month. It's okay. Okay, but we also have, of course, a scientific reason. We do things not just for fun. What is always interesting for a physicist is, for example, if a material undergoes a phase change. Because obviously something is happening for a phase change to happen, A, and B, before and after the phase change, maybe the properties are different enough to have maybe some interesting application or interesting insight. And in this case, we have here metal organic framework, which has a high spin phase at high temperatures, which is very symmetric. And we have a low spin phase. Of course, high spin also means you can in principle have, say, a magnetic moment, while the low spin phase cannot have a magnetic moment, right? So that might be interesting technologically. And the question is, how can we switch? Okay, we found a paper about a different material. But there it says, as you see on the right, it's also material with a high spin and a low spin phase. And these phases are measured at different temperatures. And they say is that in their system, they actually measure here the Raman spectrum of the CN triple bond in their material. And if you go from the high spin phase to the low spin phase, this frequency shifts by about 50 reciprocal centimeters. Okay, but this is a different material. Is that something we can always do? I don't know. I can check. All right, so I went into the computer, I calculated the Raman spectrum for both the high spin and the low spin phase in my system. And you see on the left at about 2000 reciprocal centimeter that the peaks are shifted by about 50 reciprocal centimeters, which is exactly what happened for the other material too. All right, so we know for our system, this is a usable way to distinguish the two phases, right? We can do this. Now we can go to experiment. My colleague who did the experiment, he's a high pressure guy. He put everything onto pressure. And he said, okay, temperature is bad. Temperature is bad because, for example, this metal organic framework, it's not very stable chemically. If you put it like to 200 degrees Celsius or something like this, it might decompose. So we don't want to do that, right? Pressure, different story. Okay, let's see. Left is the atmospheric pressure measurement, and he finds our 2000 reciprocal centimeter signal, as we expect, and he put like a red line through it. Now he put the system under pressure, only 5 gigapascal. It's a metal organic framework, they're not all that stable. So we measure again the signal. The red line on the right is at the same position. So you see there's again a shift of these 50 reciprocal centimeters. So our conclusion is that we can have the same phase transition either induced by temperature or by pressure. All right? So this is actually very nice. And now we can see whether that has any significance application-wise. All right. Last chapter. Optical spectroscopy is, I think, has the longest tradition of the spectroscopic methods in DFT. It's been done since the 90s. And that is a bit tricky numerically. We had some discussions yesterday after the talk about this. So basically, the exact problem for an optical transition is actually not all that easy. So what an optical transition usually entails is the following. I have a material and I have presumably all my electrons sitting happily in the valence band in the ground state. Now I have a photon coming in, it gets absorbed. And it will excite one of the electrons into a conduction band. It will now sitting up here at high energy. And it creates a hole where it was before in the valence band. Okay. So now, in principle, now what happens is that the hole, okay, basically now the electrons in the valence band had a certain number of charges. Now we remove one, the charge changed by one. You remove this this electron here to a conduction band, you add a charge there. So basically now you have a negative free charge and a positive free charge. They will interact, right? Coulomb interaction. In the very simple method, if you just take the DFT eigenvalues and wave functions and you just calculate the transition energy, you ignore that, right? But this is what we call our linear response TD-DFT. Basically, we just measure the energy difference, calculate the expectation value of the transition with that, and that is going to be slightly wrong. The exact way, using this beautiful beta-salpeter equation, the 4-point equation, basically it has 4 ingredients. It's the electron before at one position, the hole before at one position, different position, and both at after the event happened at different positions, because no one is technically required to stay where they are before. And on the right-hand side of the equation, you have Coulomb interaction and screened Coulomb interaction and all these kind of things. And that is quite horrible to solve. It's a Dyson type equation in the end, which is not so nice. Okay, but then you can get from that all the different definitions of response function and dielectric constant, which we use can use to compare to experiment. In the simplest approximation, in the first equation, that's just another Lorentz oscillator, right? We can always, in doubt, go back to that. Just to show the importance of the BSE method, I have here perovskite. This is lead iodide perovskite, where the cesium is replaced with this methyl ammonium or whatever it's called ion. I'm not a chemist, sorry. Which basically is the most popular perovskite used experimentally for solar cell applications, but it's a bit unstable. So the green one, which you hopefully can see, is the experimentally measured absorption spectrum, which is what people are interested in when they're talking about solar cell applications. And if I just try to reproduce this with normal DFT, you see the blue line. And you might think, well, that's not quite kind of so bad. Yes, I mean, it's basically where the green line is. But you see that the important thing is actually that we need to have this one done very well. This is the absorption edge. This is where basically most of the electrons are interacting with the light and can be producing electricity. And you can see that because we don't have the interaction between the hole and the electron, which is Coulomb interaction, it lowers the energy, right? So we need less energy to excite this. We actually get numerically a too high energy we need to produce these free electrons we can use for electricity. So that's bad, right? That's why we need to use BSE. But on the other hand, BSE is, and I don't go into the details, a very numerically demanding method, very difficult to converge it to the right result. So if I now use BSE in whatever fashion I can do on my cluster at home, then I see that the position of the start of the absorption I get right. So the method works. but I cannot actually go numerically to the exact accuracy I need. So what that in this case means, for example, is, well, first of all, the curve is far too wobbly, right? These wobbles in here, they are not real. They are because I couldn't do the calculation properly. And what you also see is the absorption here is too high. The absolute value is too high. And that is for the people who are in the know, I couldn't use enough k-points. The Brion zone sampling isn't dense enough. So the points you have are overestimated, overweighted. So this is a common problem. So there again, what is better? Having qualitatively wrong results of the one sort or qualitatively wrong results of the other sort, right? You may decide. The only thing you can do is get a bigger computer. But we can also, of course, look a bit more into detail. We can, for example, say, it is not only important for us what is the energy, the excitation energy the material reacts to. We are also interested in the wave function of that, what we then call an exciton, which is basically the quasi-particle describing the hole and the electron. And we can say, okay, we need to know this wave function to talk about, is this a localized or delocalized thing? So for example, if we have a very localized electron hole pair, that is going to recombine probably very quickly, right? So basically recombination is when the both at the same side. That is bad because I can only extract the electron if it lives long enough to reach the electrode, right? If it combines with its hole before it reaches the electrode, we may have had a high absorption rate in the solar cell, but we cannot extract the energy, right? So what we do is, in this case, we look at the wave function, and we see that we put the hole, we place it here right in the center, and we say that we see that the majority of the probability density for the electron is to be spherical around this. It's basically an S state around that. And that's what you expect, and it's very short. The wave function extends up to about 3 to 5 unit cells, right? That's actually not so much. So we can expect that if nothing else happens, these are going to recombine quickly, which we don't want. Okay, we can do also with this information plasmonics. So plasmonics is basically the collective motion of the electron gas. That can be interesting for a number of reasons. My favorite reason is chemical sensing. So basically every material has a frequency. I don't know whether every material has a frequency, but basically there's a frequency of the material. If you put the energy of this frequency in via light, for example, you can excite a wave, an electron wave. So the electron gas will just oscillate. And what happens is if you have an absorbent on the surface of this material, that energy changes, right? So you can tune the resonance with the absorbent. How is that interesting? Well, a few years ago was introduced little sensors you can put in your milk cartons. And it will sense when your milk is spoiled and tell the fridge that your milk is spoiled, and then the fridge can order online new milk. That has been shown already like 4 or 5 years ago as a prototype. Right? That's basically one of the possible applications. All right. Right. Okay. Here example how this looks like in graphene. Graphene you can excite, for example, here in the ultraviolet, 5 to 10 electron volts, depending on the momentum, and there's another excitation you can do around, say, 15 to 25, and these involve different electrons in the electronic structure. That is actually very similar to the behavior of graphite. It's kind of, standard. That calculation actually also took about a month to get that one picture. What you can barely see here is that there's a little bit of purple here at the bottom, which actually has been first found by a friend of mine who is now working in Colombia. And so it was very difficult to get there, but we figured out that this is actually not numerical noise, which we first thought. There's actually a third plasmon in graphene in the terahertz region. And the reason we can find this there is because graphene has a two-dimensional electron gas. And so this confinement will yield another mode for the oscillation. If you read the paper, there's also a back of the envelope model to explain this in detail. Okay, so I think, well, I think I gave you enough pretty pictures for today. So as final words, please give funding for computational science, everyone. It's so much cheaper than experiment, right? And it's so much more realistic than just relying purely on analytical methods. Don't get me wrong, theoretical people are very important. Without the basic equations, we can't do anything, right? But we can do more if we all work together. In terms of challenges for the future, not just for my personal research, but I think for the field, we have to go into non-ideal systems, which include defects and other things we find actually in real materials. But that needs more resources because we have to work with larger simulation cells. So this can be a bit of a problem. And I think we have to put a larger emphasis on multi-scale modeling to not just jump from the atomic scale directly to the macroscopic scale, because most of the time, what we see experimentally will be quite different from what we see in the atomistic modeling, because we do not take the mesoscopic structure of the materials into account. And I think that is something we have to work on. It's just very tedious to do, so most people skip it, right? And I think if we can figure out how to do this better, that would be nice. All right, that is all for today. And thank you for your attention and staying awake. Thank you.
Thank you, Robert, for your interesting talk. Now we enter the question and answer session. So I'd like to invite attendees in this room or in the Zoom. If you have any questions, please raise your hands, or I think it's better if you talk directly in the Zoom rather than type a chat. First, in this room, is there any questions, student in here? Oh, there is a question. Silakan, Pak.
Very wonderful, Dr. Robert. So my question related to exciton and plasmon, especially some technique for detect for plexiton in resonance in. So any new technique for that in computationally?
Can you be slightly more specific, please?
In the case of plasmon exciton, especially in resonant behavior, sometimes happen for plexiton. In computational, how to detect this one? Maybe you have some idea or some information about it.
I have to think about it. Maybe we can talk later. Maybe I have some idea.
Okay, thank you. Is there any other questions? Maybe participants in the Zoom? Yeah, you can turn on your microphone and directly ask Dr. Robert.
think we had the technical questions yesterday already.
Technical question.
So most people are probably happy.
Maybe I have one questions in the next page, Robert.
Okay,
In the next, can you? Oh,
this one.
this is the ELS of
Yes. Yeah.
pristine pristine graphene, right?
That is in graphene. Yeah.
Pristine graphene.
So this on the right hand side, there's also the yield,
Yields.
but for a wider spectrum,
Hmm.
right? So we have it for from 0 to 25 electron volts and 2 cuts through the Brion zone from gamma to M
So,
and from gamma to K. So these 2 directions,
I see.
right, to get the dispersion relation. So this is because the yields depends on momentum as well as excitation energy, right? So
So the key is Q means the direction of
Q is the momentum of the plasma because it's a wave.
oh yes.
Yeah. So here I just take the absolute value for plotting.
One direction only.
2 directions. That one is from gamma to M,
Oh yes.
and this one is from gamma to K.
Gamma to K.
So from the center to the short side
Mm.
and to the corner of the Brion zone. And that
In-
basically covers the important bits.
Important things.
You see, it's quite symmetric actually.
Yes, yes.
Yeah.
But in the next page, you put the different value of Q number in here.
Yes, 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 exactly. So this is over the whole Brion zone, but we have here what looks like numerical noise
Yes.
at this area here. But to be sure, we just zoomed in. So now you see we're here in the area of that's 1 electron volt, so less than 1 electron volt, right? And 0.5, 0.1, much less than 0.1 over angstrom, right? So this is this area here. So I went here up to 200 millielectron volts, so 0.2. And you can see here the momentum is actually really, really small. So I'm really zooming in into almost the optical limit. Right, so here, so I think what is the momentum of a photon in the visible spectrum? 10⁻⁵, something like this. Let me lie. Right, so we're almost at the momentum we have for the photon, right? So this is very, very small. And but basically the idea is that we actually have a non-vanishing signal, right? So it's not numerical noise. We were able to increase the resolution of the computation with some tricks to the point that we can show that this is actually, so this is now basically showing the dispersion in Q, right? Around the zone center, it's actually symmetric. It doesn't matter whether I go into M or K direction. It's because it's so small. So I have this dispersion, and where you can nicely see we have this square root Q behavior, right? So this is the dispersion of the terahertz plasmon in graphene, which experimentally has been some indication should be around, has been measured around 4 terahertz. Yeah.
Okay. So this is not a numerical error.
I hope not.
Okay. Thank you, Robert. Oh,
Let me ask Pak Fazi.
yes. Oh, Dr. Rahmat, please.
Sorry. I have a question about this ELS spectra. In graphene, there are 2 kinds of plasmon excitation. The first because of interband electron excitation and intraband excitation.
Yes.
We have ever tried to calculate ELS. My master student was done these calculations,
Mhm.
and she cannot observe the the peaks in low energy, and because when we try to see the formulations, uh, in the calculation only calculate the interband excitation in the formulations. But I found here in your presentations that you can get the intraband. So that's why the plasmon energy very low in
Yes.
terahertz region. Can you explain? Because we just published about this calculation results, and but in that publication we state that we don't observe the low energy plasmon according to the EAS calculation results.
Right. Yes. Okay. So you did everything right. The reason we were able to actually get this resolution down here is because we implemented a specific routine in the GPOR code, a grid refinement technique, where we were able to run a K-point grid locally of about 65,000 times 65,000 points.
Oh,
Locally,
I see. Okay,
right?
okay.
Not you can't do this over the whole Brion zone, so we had to have a refinement technique where you zoom in just there. So this is what we
Oh,
did numerically.
okay.
However, you could still say that this might be dodgy, and I would grant you that. So there is another paper out there which we did. Unfortunately, this is not running on my computer, so I can't you now show the slides I have for that. We also did a theoretical and an analytical description of that. And we believe that the reason we can find this terahertz plasmon is because of 2D confinement, basically. So the normal plasmons you find, these big ones too, they can be easily reproduced using, so there's a standard equation to basically get, you start with oscillating electric field, and then you put in electron density and so on, and you can get a plasma frequency.
Oh, I see.
And if you use a three-dimensional electron gas as your starting point, you get plasmons always in the energy range of electron volt. If, however,
Yeah.
however, you start with an approach where you say, I have a 2D electron gas, right? Then the equation is slightly different. Now, it's been a few years, I cannot remember, but there was one factor was different. And if you start with the 2D electron gas, you immediately get an expression, an analytical expression, which always gives you plasma frequencies in the terahertz range. So for us, that is good indication that that this is basically a property of 2D materials, right? And of course, now we have this specific extra thing that we have the Dirac cone. So I do not know whether I would take a random 2D material, whether or not I would get that in the end. But the effect is or requires a 2D electron gas, else you cannot get it.
Okay. Principally, also in our published paper, we think that the frequency of the plasma frequency depends on the number of free electrons. And we found that the number of free electrons is small, and that's why the plasma frequency in terahertz region, not in UV like
Right.
in a metal.
Right.
Okay.
Okay. Thank you.
Sorry, I don't open my webcam.
No, this was a very good discussion. Yes.
Maybe I will share my our paper to Dr. Fahzi, and please look at and give an advice how we can improve this.
Of course. Pleasure.
Okay, thank you, Dr.
Thank
Robert.
you. Thank you.
Okay, thank you, Dr. Pak Rahmat.
I have a question. I lost the part when you make some in desalination, yeah,
Yes.
between DFT and could you show the
Yes.
this one?
Almost there. There you go.
Oh, yes, this one. Yeah, I missed this part when I went out. So, what kind of combination did you do with this one?
All right. So this, okay, so the main part of that project was actually looking at this setup of molybdenum disulfur sheets in the membrane and the water with ions trapped inside. And this one here, this sheet has a hole in the center of this shape. And basically, the main point of the study was to change the diameter of that hole from 1 to 5 angstrom, roughly, to see the effect on the diffusion of the water and the ions through that. Now, in that specific project, DFT was more used as a cross-check, just to make sure that that no unexpected effects are happening. So I'm not 100% convinced that that this is a perfect simulation. So, for example, in this model here, I think there was no
in between you use explicit molecule there.
Yeah, that's explicit molecular dynamics. Yes, using Reac's FF potential, and I think the water itself was modeled just with a simple interactive potential, so it's not reactive, and there's not a good interaction between the molybdenum surface and the ions, right? So now basically, because it's really difficult if you don't have a potential for these given in molecular dynamics, making those is not an easy task, right? So what then the colleagues in engineering decided, because it needs to be done quickly, is to go the other way around, to check whether or not there is a significant interaction between certain components of the system, right? And then if they find that there is not a significant interaction that would inhibit the validity of the MD simulation, then basically say like it's good enough, right? So for example, you would say here, what is the surface interaction of the water and the MOS2? What is the interaction of the water with certain kinds of defects, right? So now obviously here, we are working in the MD with defects which are of a larger size, right? So like 5, 6, 7, 8 atomic size. But with the MD, you can, with the density functional theory, you can create a smaller defect. And basically what you need is a reactive site, right? So it doesn't really matter whether you have 20 atoms missing or 3 atoms missing, you want a reactive site. So you create a reactive site by producing a defect in the molybdenum disulfur, and you see whether the water, for example, would have any meaningful interaction, right? Because that, of course, could mean that you have the clogging up of your porous membrane, right? Or some other effect which would change the diffusion coefficient, right? So we don't want that. Apparently, they did not find such an interaction, so everyone was happy with the measured results.
Oh, yeah, very interesting. So you do not in parallel, yeah, first with DFT or MD, and then not using a carparenil or something like that.
No, these were more or less independent.
I see. I see.
Yeah. Yeah.
Okay, thank you.
Thank you, Pak Acep. Is there any questions, student or participants in the Zoom? Okay. If there is no questions, maybe I will have to say thank you. Please give applause once again for Robert. Finally, we reach our final schedule in this colloquium series from Computational Science Department. Again, thank you for your attendance and attention. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.